I want you to assume Mr. Evans goes back to railroad work, and that he's currently working on the railroad, which I believe he gave you by history.
That is correct.
And that he's performing these tasks on a daily basis, and let's roll through them very quickly. Bending down to couple air hoses, pulling cut levers, tying handbrakes, opening knuckles, tying handbrakes, mounting ladders, throwing ground throw switches, which I believe the description has been about a 25-pound ball at the end of a lever through a course of 180-degree arc. I want you to assume he's got to perform and riding on a ladder. He's got to perform these tasks on a daily basis, 8 to 12 hours a day. The force of that work, assuming he's continuing to do it, what is the likelihood that he's going to have surgery?
I'd say very likely.
Is it more than 50%?
Yes.
Do you hold that opinion to a reasonable degree of medical certainty?
Medical and engineering certainty.
And I want to talk about, we've covered your medical analysis. I want to talk about your biomechanical analysis. And
sure.
Tell us what you did for a biomechanical analysis of this same patient, knowing that he's been through this trauma of a train-on van.
Well, basically we use Newton's laws of physics. There is a lot of energy transferred from a train to a van, even though the train is only going 8 miles an hour. And calculation is not actually that hard to do. So you got the train tracks, and you got the van, and then you got the big train going in that direction. He's sitting here and hits the van doing 8 miles an hour. Well, essentially all the energy is going to be transferred to the van because it pushed it 50 feet. And keeping in mind that this is 2 tons worth of metal that you're pushing 50 feet, that's a lot of energy being transferred. Okay, so what does that really mean? Well, if you think of energy being transferred, if there's too much energy transferred, then someone can get hurt. Okay, and energy comes from mass times velocity, or more apropos, change in velocity. So you can appreciate, since they were going in this direction initially, and this train hits them this way, he's being pushed in this direction. He's going 0 miles an hour in this direction initially, okay? And then all of a sudden he's going 8 miles an hour, almost instantaneously. It takes about 1/10 of a second for all the energy to be transferred from metal to metal, because energy transfers at the speed of sound in metal. Okay, so that's 700 feet a second. Well, there you have it. It's very, very short. So about 1/10 of a second. So you do 8 miles an hour, and I'm just going to put the calculations up here for you, times 5,280 feet per 1 mile, times 30. 1 hour equals 3,600 seconds. So you can see that the miles cancel, the hours cancel. So you have so many feet per second, okay? And so that's I turned off my phone, I don't have my calculator. But in any event, that's going to be 1.3 times 8, 10.4, roughly about 10.4 feet per second. So that's the velocity, okay, that he's going in this direction after the crash. Before the crash, he was going 0, so the delta V, the change in velocity, is 10.4 feet per second. It occurred over 0.1 seconds, so 1.1 second. So now you have 104 feet per second squared. And the way that you calculate G is just divide that by what G is, our acceleration towards the center of the Earth, which is 32.2 feet per second squared. And that equals about 3.6 G. So that's the acceleration that got hit from the side. So basically, he was thrown in that direction. His body was, because he's attached to the car or the van, and his head, since you got the neck here, it's not attached to the vehicle. So it's going to go fling in this direction, and then his torso is going to be flinging in this direction as well.